All right, ladies and gentlemen, so you've gotten some introduction into our three major classifications of reactions, which is redox, precipitate, and acid-base. Now what we're going to do is we're going to specifically look at redox reactions only, get a little bit more in depth into how we identify them, how we track those electrons, how we assign oxidation numbers, looking at half reactions. So make sure that you're ready to do this and you're sitting somewhere that's quiet, because the information in here gets a little bit more complicated than what it was last time. All right, so, and make sure that you're also, if you have questions, you don't understand something, make sure you're putting your questions over there on that left-hand margin of your Cornell notes as we go through this. So here we go, identifying redox reactions. You found a reaction, you saw it had a single element, you said, okay, well, I think that's going to be a redox reaction, now what? So remember, with redox reactions, it's actually a transfer of electrons. There's going to be a net change in oxidation state of a particular element from the reactant side to the product side. So the only way to do that and figure out what's what is we need to assign oxidation numbers to each element in the reaction. And oxidation numbers are going to tell us this charge, quote unquote, so that we can track where electrons are going and where they're coming from, because we know basically, just from our general knowledge, that if something's going to gain electrons, it's going to become more negative. If something's going to lose electrons, it's going to become more positive. And then remember the mnemonic that we introduced last time, oil rig, right? Because remember, we've got these half reactions. We've got a reduction reaction and an oxidation reaction. And the oxidation reactions is the one that's going to lose electrons, right? Because remember, oxidation is loss. So, and then reduction is gain. So this guy's going to lose electrons, this guy's going to gain electrons, and the transfer is going to be in that direction. So, and something else I want to touch on, this is just a basic concept, but what's the difference between an oxidation number and a charge? Because we've kind of been using those words interchangeably throughout the year so far, and I think now it's time to actually make this distinction. There's a slight difference between the two. Oxidation numbers are theoretical numbers. They don't actually really exist. All right? So oxidation numbers are based on electronegativities, right? How attracted are elements to electrons? How likely are they to take an electron from another element? And so we assign oxidation numbers to these elements inside of a compound when they haven't actually gained or lost, or anybody's taken those electrons. So that's why we say my oxidation numbers are theoretical numbers. And what we're trying to say is, hey, if I did go in there and I ripped those elements apart, who would get the electrons and who would be left without them? All right, and that's what an oxidation number. A charge, on the other hand, a charge occurs when I actually do have elements that have split apart, and there's an actual transfer of electrons that has occurred, and you have an actual charge based on that transfer, right? So oxidation numbers are theoretical, like what would happen if I broke apart the elements. A charge is a charge. It means that it has broken apart, the transfer of electrons has happened. All right, so slight difference there. It's not really important. I just don't want you to get confused with the terminology here. I need you to know specifically what each one of those represents. All right, so my rules for assigning oxidation numbers. This is where a lot of people get kind of tripped up every year, and it's because they just don't memorize the rules. The rules aren't inherently complicated. They're actually pretty simple. And so we'll run through these really fast, and then we'll show you some examples, and I'll go through some examples with you on this particular PowerPoint or this particular lecture. So the first one, the oxidation of an atom. So the oxidation number of an atom in a free element is 0. So this is an element by itself, is what you want to notate there if you don't understand that. So I go over and I look at my examples. I've got copper, right? Well, it's a solid, it's by itself, so the oxidation number of copper would be 0. And I'm going to put my oxidation numbers up top where I was putting my charges before. So the oxidation numbers always go up top so that I do not get them confused with subscripts. So the other example here is O2. Well, O2 is paired with itself, but this is a diatomic molecule, and so it is still considered to be a free element, and so I'm still going to say that the oxidation state of that particular, of each of those oxygens is 0, right? Okay, so moving on. The oxidation state of a monoatomic ion is equal to its charge. So this word monoatomic means I've got an atom that's by itself. Right? So monoatomic, I've got a monoatom. I've got an atom by itself. It's an ion. And so when I look here, calcium, it's got a 2+ charge, right? That means this has already had the electrons transferred. And so if I have a charge up here already, that means my oxidation state is equal to my charge, right? And so the other example is chlorine. I've got a chloride ion here. It's Cl minus. That means my oxidation state is going to be minus. So if I've got an ion, the oxidation state is the charge of the ion. All right, moving on. Number 3, hydrogen is generally +1 oxidation state. And I want to make sure that you understand this word generally. It doesn't mean it always is. It means most of the time it's going to be +1. All right, and the exception to this is when it is a hydride. So you've got to go back to your naming forms, right? And so if I looked at these particular compounds, well, I'm going to name them. The name of this particular compound here is hydrochloric acid. It doesn't have the word hydride in the name. Therefore, in this particular compound, my hydrogen would be a +1 oxidation. All right. Now I look at the other examples. If I name this compound here, NH3, I'd actually have nitrogen trihydride. So nitrogen trihydride, if I'm naming this, notice I've got the word hydride in the name. And so in this compound, the hydrogen will be a -1. And so your hydrogens are either going to be +1, -1. Most of the time they're going to be +1. But if they're a hydride, that's when you get to your -1. And then another really simple thing, guys. Notice this hydrogen's in front, this hydrogen's at the end. So, and if a hydrogen is the last element in the compound, we are going to name it a hydride, right? So that's your rule here. If the hydrogen's at the end of the molecule, it's a hydride, and it's going to be a -1 oxidation. All right? Next one, oxygen is generally a -2 oxidation state. And again, the word generally here, right? That means not always, but most of the time, oxygen's going to be -2. And the exception to this is when it's a peroxide. Right? So when it's a peroxide, and this is something that I'm going to go ahead and state here, these rules are going in order of importance, right? So rule number 3 will trump rule number 4, rule number 2 will trump number 3, and number 1 is the end-all be-all absolute, right? So what we're looking at here is I'm going to look at water. So this particular compound here, I've got hydrogen here in front, so I know based on rule number 3, it's going to be a +1. I've got 2 of them, and then based on my rule number 4, my oxygen will be a -2. All right? So oxygen's -2 because the hydrogen's +1, and we're moving on. All right? So I'm looking at the next compound. Again, rule number 3 tells me that my hydrogen is a +1. All right, I've got 2 of them, and then it's kind of jumping between 4 and 5 here, but I'm just going to go ahead and tell you there's no charge on this molecule, so that my charges all, or my oxidation numbers all have to add up to 0. And so if we look at this, I've got each hydrogen is +1, but I've got 2 of them. So I have a total of +2 on this molecule for my hydrogen, so that means I've got to have a total of -2 for my oxygens. Again, this goes back to formula writing, right? Same kind of deal. And that means in this particular compound, my oxygen would have to be -1, right? And then what that's going to tell me is based on assigning these oxidation numbers that this is a peroxide. And what we do is we actually get the first element and get that name, so that's hydrogen. And so this compound is named hydrogen peroxide. It's a peroxide because your oxygen is -1. All right? So the only 2 oxidation states for your oxygens is -2 or -1. All right? It's -2 95% of the time. It's -1 in your peroxides. Okay? Number 5, the sum of the oxidation states in a molecule is equal to the charge of the molecule, right? So we've seen this. We have done the water already. We've done the water already. We know that my hydrogen's +1. We know that my oxygen's -2. So my hydrogens add up to +2. My oxygens add up to -2. And they add up to 0 because they cancel out, right? And that should be the case because I don't show a charge on here. Now my sulfate ion over here, I've got a -2 charge, and so all the oxidation states here should add up to this -2. Well, I'm going back to my rules. I know oxygen's -2. I have a total of -8, right? Because I have 4 oxygens, which means I need a total of +6, right? Because 6 minus 8 is -2. I need these 2 numbers to add up to -2. That's where I got the +6 from, which means my sulfur is going to be a +6 oxidation state. All right. And then number 6, in compounds, metals have a positive oxidation state. This is true all the time. Metals are not going to have a negative oxidation state. And then your group 1 metals are always +1. Your group 2 metals are always +2. So I can go over here. I know sodium's in group 1, so I know it's going to be +1. I know calcium is +2, so because it's in group number 2. And that's always going to be the case, guys. Simple, simple, simple. All right? Make sure you have these rules memorized before you come into class next time so that we can actually do the practice and you're, you know, it's not that this is something, if you don't understand, write down a question. But if it's about you not memorizing this stuff, we're gonna have some issues in class. All right, so now I'm going to go through some practice. I'm going to go really fast with this, guys. As a matter of fact, I'm going to go ahead and these is just identify, because all I do here is I ask you to identify the following types of reactions. So I'm asking for, is it composition, decomposition, combustion, single replacement? These are my sub-reactions or subtypes for my redox reactions. I'm going to go ahead and pause this video, and I'm going to write the answers down. I want you to pause it, and I want you to see if you've memorized what a synthesis reaction is, what a decomposition reaction looks like, what's a combustion reaction look like, what does a single replacement reaction look like, all right? So I'm going to pause it and write the answers down. I'm going to come back on. We're going to talk about it just briefly. All right, guys, so I've got the 4 answers here. This first one, synthesis, I've got 2 reactants forming 1 product. That's the definition of synthesis. Number 2, I've got 1 reactant, breaks down to form multiple products. That's the definition of decomposition. Third one, I've got a molecule, I've got oxygen, reacts to form H2O and CO2. That's the definition of combustion reactions that I gave you. And then the last one, I've got zinc and a molecule, so I have a single element in a molecule, and then I look over in the product side, and zinc is all of a sudden paired up. And the H is by itself. So what happened here is zinc went and knocked out the hydrogen, right? So a single element got replaced. So it's single replacement reaction, all right? And here we go. Hopefully if you didn't get that, go back and listen to the explanations and then go back and look at your previous set of notes and look at those definitions that you have copied down. And you'll notice all I'm doing is just using a definition and applying it. All right, so here we go again, labeling oxidation numbers. I'm going to pause it, and I'm going to label each one into the 4 reactions, and we'll go and discuss each one by themselves, all right? So make sure that you've got this stuff down. I'm going to do number 1, and then you'll pause it and check your answers against mine. I'll do number 2, you pause it, check your answers against mine. Number 3, pause it, check my answers, so on and so forth, all right? So here we go with number 1. Write down the reaction, assign your own oxidation numbers, see if you can do it, and see if we get the same answers. All right, so for number 1, notice I've got hydrogen is 0, oxygen is 0. On the other side, I've got hydrogen is +1, oxygen is -2. I'm just using rules 1, 3, and 4, I think, right? Single elements by themselves, 0. Single elements by themselves is 0. Hydrogen's generally +1, oxygen's generally -2. That's all I did. All right, so now go ahead and write down number 2. I'm going to go ahead and pause it. I'm going to go through number 2 with you. Actually, you try it and then check your answers against mine. All right, so here we go. I've got, in this compound here, I'm using the rule that oxygen is generally -2. My silver, since I've got 2 negative charges, I know that these have to add up to -2, and I've got 2 molecules here, so each one has to be +1, right? Because I need 2 positives here to cancel out the 2 negatives. And then for my products, my silver is by itself. It's a monoatomic element. So here we go, that's 0. And then my oxygen is also by itself, so it's got the oxidation state of 0. All right, again, just using my rules, right? In this one, we're introducing something new because my oxidation numbers have to add up to 0 because it is a neutral compound. All right, and I knew what oxygen was, and then I just back calculated to figure out what silver was. All right, so now let's move on. I'm going to do number 3. You write down number 3, check your answers against mine. All right, so here we go. I've got all of them labeled. Again, I'm just using the rules. So I go here, and I'm going to start. In this compound, if you don't know where to start, guys, hydrogen has a rule, right? So I'm going to name this compound because this hydrogen's at the end of the molecule, so this would be carbon tetrahydride. So I know since it's at the end here, it's a hydride, so my hydrogen would be -1. Well, I've got 4 minuses here, and so that means my carbon, in order to cancel this out, has to be +4 because notice there is no charge on this molecule, so all my oxidation numbers should add up to 0. 4 negatives, I need 4 positives, which makes carbon +4. Moving on, I've got my oxygen. It's an element by itself, so its oxidation state is 0. Going to the product side, I'm going to start with hydrogen. It's at the front. It's not a hydride, so that means it's going to be a +1, right? My oxygen is not a peroxide. It's -2, all right? And then last one, CO2, carbon monoxide. I'm going to start with my oxygens. I know they're generally -2, so I've got a total of 4 negatives here, guys. And then that means my carbon has to be +4 because they have to add up to that 0. All right, because it's a neutral molecule. All right, here we go. We're going to do the last one. This one's a little bit more complicated. So Write it down, see if you can get it. Every single element has to have an oxidation number. All right, so even if we have a compound here that's got 3 of them in it, you're going to have 3 oxidation numbers here, okay? So let's go through this. All right, so here we go. Zinc is by itself, so I'm going to give it a 0. My hydrogen is by itself. I'm going to give it a 0 because I'm going to start with the easy ones. Then I'm going to go to H2SO4. So I know hydrogen's not at the end of the molecule, so it's going to be +1. I know oxygen is going to be a -2 here. And so I've got a total of 8 negatives. And this is where it gets kind of goofy. I've got a total of 8 negatives from my oxygen, so I need these 2 molecules to add up to 8 positives. Well, I know I've got 2 positives here, and then that means my sulfur has to be +6 to get me to the +8, because, look here, guys, this is a neutral compound, so all my oxidation numbers should add up to 0. And if you're just listening to this and you're confused, write some of this stuff down, guys. Where'd I get the -8 from? How do I know that these 2 molecules need to add up to +8? How come that's +2, right? That kind of stuff is the things that I expect you to know from doing your formula writing stuff. All right, and then I'm going to come over here. I actually left the oxidation number off of zinc, so again, I'm looking at this compound. I've got 8 negatives here. I know my sulfur's +6 because it's over here, it's +6, and my polyatomics never change oxidation numbers. Write that down, write it big, put your mama's name next to it. Polyatomics never change oxidation numbers, right? So if I know sulfate over here, I know sulfate over here is going to have a +6 and a -2. All right, so again, I've got 8 negatives, which means my zinc in this particular compound is going to have to be +2. All right, because I need a total of 8 positives to cancel out these 8 negatives. All right, and that's it. We're moving on.